In number 1, we'll need to use one of the angle sum or difference identities. And this fits the pattern of sine A times cosine B plus cosine A times sine B, which is equal to sine of A plus B. So this is equal to sine of 21 plus 4, or sine of 25 degrees. In number 2, this fits the pattern of cosine A times cosine B minus sine A times sine B, which is equal to cosine of A plus B. So the expression is equal to cosine of 170 plus 8, or cosine of 178 degrees. In number 3, this fits the pattern of tangent A minus tangent B all over 1 plus tangent A times tangent B, which equals tangent of A minus B. So this expression is equal to the tangent of 25 minus 20, which is equal to the tangent of 5 degrees. The expression in number 4 fits the pattern of sine A times cosine B minus cosine A times sine B, which is equal to the sine of A minus B. So this expression is equal to the sine of 80 minus 7, or the sine of 73 degrees. In number 5, we're going to go a step further by finding the exact value of each expression. So sine of 20 times cosine of 10 plus cosine of 20 times sine of 10 is equal to the sine of 20 plus 10, which is equal to the sine of 30 degrees. And the sine of 30 degrees is equal to 1/2. And if you need, you can draw a reference triangle for the sine of 30 degrees with an opposite side 1 and a hypotenuse 2 and adjacent side square root of 3. In number 6, we have cosine of 100 times cosine 10 plus sine of 100 times sine of 10, which is equal to the cosine of 100 minus 10, because that's a cosine of A minus B, and that's equal to the cosine of 90 degrees, and the cosine of 90 degrees is 0. In number 7, the tangent of 25 plus the tangent of 20 divided by 1 minus the tangent of 25 times the tangent of 20 is equal to the tangent of 25 plus 20, which is equal to the tangent of 45 degrees, which is equal to 1. In number 8, 1 over the cosine of 10 times the cosine of 35 minus sine of 10 sine of 35 is equal to 1 over, and the denominator portion of this is the same as the cosine of 10 plus 35. So this would be equal to 1 over the cosine of 45 degrees. The cosine of 45 degrees is 1 over the square root of 2 in unrationalized form, so when I flip that to form the secant, we'll get the square root of 2. In 9 through 10, we have given angles A and B with descriptors, and we're evaluating each angle sum or angle difference expression. So in angle A, I'm going to want to make a sketch of it. It's a first quadrant angle between 0 and 90. And the cosine of angle A is 3/5. So that means that angle A is that angle right there, and the cosine is 3/5, so adjacent over hypotenuse is 3/5. That's going a 3, 4, 5 triple, so that gives us an opposite side of 4. Now let's make a drawing for the second angle, which is angle B. So angle B is an angle that falls between 270 and 360 degrees. That means it terminates in quadrant 4. And this time the cosine is equal to 4/5. So if this is angle B, that's adjacent over hypotenuse. That's also a 3, 4, 5 right triangle. And so our missing side there is -3. Remember, it's hanging down, so that opposite side will be negative. And in number 9, we're asked for sine of A plus B. Sine of A plus B is equal to sine of A times the cosine of B plus the cosine of A times the sine of B. And now we just have to look at our drawings. Look at the drawing of angle A. The sine of angle A is 4/5. Look at the drawing for angle B. We need the cosine for that one. The cosine of angle B is positive 4/5. And now we need the cosine of angle A. The cosine of angle A is adjacent or over hypotenuse, so that's 3/5. And then the sine of angle B is opposite over hypotenuse, so that's -3/5. Now we just need to do the arithmetic. So 4/5 times 4/5 is 16/25, and 3/5 times -3/5 is -9/25. And if we do that subtraction, we get 7/25. For number 10, tangent of A minus B is equal to the quotient tangent A minus tangent B all over 1 plus tangent A times tangent B. So now we're going to want to refer to the drawings. Tangent of angle A is opposite over adjacent, so that's 4/3. Tangent of angle B is opposite over adjacent, so that is -3/4. Downstairs, the same two numbers, so 1 plus 4/3 times -3/4. All right, and what we can do is just address all of the arithmetic. So we have 4/3 plus 3/4. I'm going to give them a common denominator of 12ths. So that would be 16/12 plus 9/12 on the top. And downstairs we have 1 plus, and we have 4/3 times -3/4, which is -1. So 1 plus -1, and that's going to give us a 0 in the denominator. So that's going to be an undefined result. In number 11, we have a similar setup here. We have two angles A and B that are described, so we need to begin by making a sketch for each. In the first angle, angle A, is described as an angle between 90 and 180. So that means that's a second quadrant angle. And sine of angle A is 8/17. So that's our angle A. And sine is opposite over hypotenuse. That's an 8, 15, 17 triple. So that means that our adjacent side will be -15. And similarly, we need to make a drawing for angle B. Angle B is between 180 and 270 degrees, so that means it's in the third quadrant. And for angle B, the cosine is equal to -3/5. So I'm going to draw my reference triangle. And the cosine is -3/5, so that's adjacent over hypotenuse. That gives us an opposite side of -4, 3, 4, 5 triple, but our opposite side should be negative when we're in quadrant 3. Now that the drawings are made, we can find the values in 11 and 12. Tangent of A plus B is tangent of A plus tangent of B divided by 1 minus the tangent of A times the tangent of B. And now we just need to make substitutions for those values. Tangent of angle A is opposite over adjacent, so that's -8/15. tangent of angle B is opposite over adjacent, so that's -4 over -3, which is positive 4/3. And then downstairs, we use those same values, 1 minus -8/15 times 4/3. Okay, so we just need to perform some arithmetic here. We have -8/15 plus, and give this one a common denominator, that's 20/15. And then downstairs, we have 1 plus 32/45. So we have a little bit more arithmetic to do. I'm just going to go up here and do that. -8/15 plus 20/15 is 12/15. And then downstairs we have 1 plus 32/45. That's 45/45 plus 32/55. 45/45 plus 32/45 is 77/45. So we have 12/15 divided by 77/45, which is times 45/77. 15 goes into 45 3 times. So now multiplying, we have 36/77 for a final answer. In number 12, we have cosine of A minus B, which is cosine of A times cosine of B plus sine A times sine B. Cosine of angle A is adjacent over hypotenuse, that's -15/17. Cosine of angle B is adjacent over hypotenuse, that's -3/5. Sine of angle A is opposite over hypotenuse, that's 8/17. And sine of angle B is opposite over hypotenuse, -4/5. Now we need to perform our multiplications here first. 15 times 3 is 45. So we have 45. 5 times 17 is 85. And then our next fraction, 8 times -4 is -32. And same denominator. So now we just need to subtract or add those fractions or subtract them depending upon how you're thinking of that. And that will give us 13/85. For 13 through 18, we need to prove each trig identity. I'm going to start on number 13 with the statement that sine of theta times the cotangent squared of theta plus sine of theta is equal to the same, sine of theta times cotangent squared of theta plus the sine of theta. On the right side, we're going to transform, and I'm going to do so by factoring. I notice that sine of theta is a common factor in both of those terms, and if I factor that out, we get cotangent squared of theta plus 1, and then the cotangent squared of theta plus 1 is equal to the cosecant squared of theta. That's one of our Pythagorean identities. And if we look at the target is cosecant of theta. So sine of theta can be written as 1 over the cosecant of theta. And then cosecant squared of theta is cosecant squared of theta over 1. Now we can cancel some common factors. One factor of cosecant in the numerator and one in the denominator, and that equals cosecant of theta. And I'm just going to bring down the statement on the left side of the proof, as long as you have that left side written in on your first and last steps. You may use an arrow in between. In number 14, we have sine of theta times tangent of theta plus cosine of theta is equal to secant of theta. So I'm going to start my proof by stating that sine of theta times the tangent of theta plus the cosine of theta is equal to itself, sine of theta times the tangent of theta plus the cosine of theta. On the right side, we can transform. So sine of theta can be rewritten as sine of theta over 1. Tangent of theta can be written as sine of theta over the cosine of theta using the quotient identity. And then cosine of theta is cosine of theta over 1. Now, if I want to add these fractions, once I'm finished with the multiplication, I'm going to multiply that second fraction by cosine of theta over cosine of theta so that we have a common denominator. So sine of theta times sine of theta is sine squared of theta over 1 times cosine of theta is cosine of theta. And for the second multiplication, that's cosine squared of theta over cosine of theta. And when we add fractions, you add the numerators, sine squared of theta plus cosine squared of theta, and keep the denominator, which is cosine of theta. One of the Pythagorean identities states that sine squared of theta plus cosine squared of theta is equal to 1. So this is equal to 1 over the cosine of theta, and 1 over the cosine of theta is equal to the secant of theta, and that's what we were trying to prove. So I'm just going to bring down the left side of my identity, sine theta times tangent of theta plus the cosine of theta is equal to secant theta, so that we have our initial statement complete and the final statement complete. All right, in number 15, we're going to start with the negative natural log of tangent of theta is equal to the negative natural log of the tangent of theta. We're going to use a log property. When there's a multiplier or coefficient of a natural log, you can move it into the exponent of the argument of the log. So this is natural log of the tangent of theta raised to the negative 1 power. When I raise anything to the negative 1 power, it is finding its reciprocal. And its reciprocal would be 1 over tangent of theta. And 1 over tangent of theta is the cotangent of theta. And so I'm just going to bring the left side of that statement down to the final statement, which is what we were trying to prove. In number 16, we have sine of theta plus cosine of theta squared plus sine of theta minus cosine of theta squared equals 2. So I'm going to start by writing sine of theta plus the cosine of theta squared equals sine of theta minus the cosine of theta squared. Oops, I'm sorry, that is plus, and then that equals sine of theta plus cosine of theta, the quantity squared, plus sine of theta minus cosine of theta, the quantity squared. On the right side, we can perform the squaring. So if you can write out both factors, but this is sine of theta plus cosine of theta times sine of theta plus cosine of theta, and then FOIL. And if we FOIL, the first term is sine squared of theta. The middle term is the sum of both the outer and inner products, which are each sine theta times cosine theta. So that's plus 2 sine of theta times the cosine of theta. And then plus the product of the lasts, which would be cosine squared of theta. So that's the first parentheses multiplied out. The second parentheses multiplied out, if we do that similarly, is sine squared of theta minus 2 times the sine of theta times the cosine of theta plus the cosine squared of theta. what you'll notice is that we have two pairs of opposite signed terms. Positive 2 sine theta cosine theta and negative 2 sine theta cosine theta. So those are going to go away, and we'll be left with sine squared of theta plus cosine squared of theta plus sine squared of theta plus cosine squared of theta, which is equal to, by the Pythagorean identity, 1 plus 1, which is 2. So bringing down the left side, that's sine of theta plus the cosine of theta squared plus sine of theta minus cosine of theta squared equals 2. In number 17, we have a similar sum and difference identity to use. So I'm going to start my proof with a statement that should be intuitively obvious, and that is cosine of 270 degrees plus x plus cosine of 270 degrees minus x is equal to the cosine of 270 degrees plus x plus the cosine of 270 degrees minus x. In other words, the statement on the left is equal to itself. Now we're going to transform the statement on the right. Cosine of 270 minus x is cosine 270 times the cosine of x minus the cosine of 270, minus the sine of 270 times the sine of x. And then the second expression, cosine 270 minus x, is cosine 270 cosine x plus sine of 270 sine of x. You'll notice we have a pair of opposite signed terms. Those will add up to 0. And what we're left with is 2 times the cosine of 270 times the cosine of x. The cosine of 270 degrees is 0. So 2 times 0 times the cosine of x is 0. And now we just need to bring down the left side of the equation. All right, the last proof looks very complicated. Let's see if it actually is. So I'm going to start with the sine of a plus b plus the sine of a minus b all over the cosine of a times the cosine of b is equal to itself. Sorry for the lousy handwriting. And then on the right side, what we can do is use our angle sum and angle difference identities to re-express what we see in the numerator. So sine of a plus b is sine of a times the cosine of b plus the cosine of a times the sine of b. And then sine of a minus b is sine of a times the cosine of b minus cosine of a times the sine of b. And you'll notice that we have two opposite signed terms in that numerator. Those terms are opposites. So in our next step, when we combine, we're going to get 2 times the sine of angle A times the cosine of angle B divided by the cosine of angle A times the cosine of angle B, which is equal to 2 times the sine of angle A over the cosine of angle A times the cosine of angle B over the cosine of angle B. And so what we can see here is that this is equal to 2 times, and sine A over cosine A is tangent A, and cosine B over cosine B is just 1. So this final result is just 2 times tangent of angle A. I'm just going to bring down what was on the left side of the identity, which was the sine of A plus B plus the sine of A minus B all over cosine A cosine B is equal to 2 times the tangent of A, with my arrow in between to indicate that that expression carries all the way down.